So in this video we're going to introduce Cramer's rule and then use it to solve a system of equations. And what's interesting about Cramer's rule is it gives us a method for solving a system of equations that utilizes only determinants. So the idea is if ax equals b is a system of n linear equations in n variables, so that way we get an n by n coefficient matrix A. So as long as the determinant of A isn't 0, then the system has a unique solution, which we've already seen. Cramer's rule, though, gives an interesting way of coming up with that solution. So Cramer's rule says that this solution vector x sub 1, x sub 2, in your n by n system all the way down through x sub n, can be found by taking the determinant of A sub 1 divided by the determinant of A, determinant of A sub 2 divided by determinant of A, and the determinant of A sub n divided by the determinant of A. And all these A sub i's are, A sub 1, A sub 2 through A sub n, all the A sub i's are is you take the ith column of the coefficient matrix A and you replace it with the vector B. And then you calculate the determinant of the resulting matrix. So the proof of Cramer's rule, which I've included here for you to read through, notice that the proof of Cramer's rule relies on this new formula that we have developed in this homework for A inverse, namely that the inverse of A can be found by taking 1 over the determinant times the adjoint matrix. So Cramer's rule is, in a sense, comes to us as a result of this new way of defining A inverse. So let's just step through a simple application of Cramer's rule. So for Cramer's rule, you need the determinant of A. So the first thing to do is to figure out what the determinant of A is. And A is just the coefficient matrix. So we want to read in the coefficient matrix. We get 1, negative 2, 1. And then we get 1, 0, 1. And we have 1, negative 2, 0. So 1, negative 2, 0. And of course we can calculate the determinant with the cofactor expansion using any row or column that we want. I'm going to use row 2. So we have that plus minus pattern. There we go, got my pin back. So we have the plus minus pattern, so plus minus, so it's going to be minus 1 times the determinant of the minor matrix for row 2, column 1. So we eliminate column 1, row 2, and the matrix that's left is negative 2, 1, and then negative 2, 0. Plus minus plus minus. We don't need to worry about the 0. I used it because the 0 times the minor matrix will be 0. So we'll get minus 1 times the determinant of the minor matrix when we eliminate column 3 in row 2. So what would be left if we did that would be 1, negative 2, 1, negative 2, and 1, negative 2. And calculating this, we get the opposite of negative 2 times 0 minus negative 2 is going to be a plus 2, minus 1 times negative 2 is negative 2, minus a negative 2 is going to be plus 2, so that zeroes out. And so we get a negative 2 for the determinant of A. And because the determinant isn't 0, there will be a unique system to this solution, and we can use Cramer's rule to find that unique solution. So the next step is to compute the determinant of A sub 1, the determinant of A sub 2, and the determinant of A sub 3, because we have a 3 by 3 system of equations. So calculating A sub 1 means take your vector B. So we have a system that can be written in matrix form as AX equals B, and in that case B would be equal to the column vector negative 1, 3, and 6. So for A sub 1, you replace column 1 of A with B. So we replace 1, 1, 1 with negative 1, 3, 6. And then we keep the remaining 2 column vectors unchanged. So negative 2, 0, negative 2. And 1, 1, 0. 1, 1, 0. And then we're going to calculate the determinant of this, so I should put in the vertical bars. We need to calculate the determinant of the matrix A sub 1. And again, we can use any row or column we want. This time I think I'm going to use column 3. So the expansion is going to be plus minus plus, so it'll be positive 1 times the minor when we eliminate row 1, column 3. So 3, 0, 6, negative 2 would be left. 3, 0, 6, negative 2. And plus minus, it's going to be minus 1 times the minor for column 3, row 2. And so if we cross those, we'll get a negative 1, negative 2, and a 6, and a negative 2. And so from here we get negative 6 minus 0 is negative 6 minus negative 1 times 2 is 2 minus a negative 12 is plus 12. It's going to equal negative 6 minus 14, which is a negative 20. And then we need to calculate A sub 2. So to calculate A sub 2, we want the determinant of, we keep the matrix A, but we replace column 2 with B. So we're going to get the 1, 1, 1 and the 1, 1, 0, but the negative 2, 0, negative 2 will get replaced with negative 1, 3, 6. And if you're curious why this works, read the proof on the previous slide. So equals, again, I'm going to expand in terms of column 3, so plus minus plus, positive 1 times the minor matrix that's left when we strike row 1, column 3. So what's left is a 1, 3, 1, 6. It went plus minus 1 times the minor when we eliminate column 3, row 2. So if we do that, we'll be left with 1, negative 1, and a 1, 6. 1 times 6 minus 3 times 1 minus parentheses 1 times 6 minus negative 1 times 1 is going to give us a plus 1 there. So we get 6 minus 3 is 3 minus 6 plus 1 is 7. So we get a negative 4 from there. And finally, we have to calculate the determinant of A sub 3. So again, we keep the first two columns now. We get 1, 1, 1, negative 2, 0, negative 2. And then we're going to replace column 3 with B, which is negative 1, 3, 6. We get to expand this however we want, so I'm going to do it with respect to row 2. So we're going to get plus minus 1 times the minor when we eliminate column 1, row 2, which will leave us with a negative 2, negative 1, negative 2, 6. Plus minus 3 times the minor when we strike column 3, row 2, which will leave us with 1, negative 2, 1, negative 2. So we're going to get the opposite of negative 2 times 6 is negative 12, minus 2 minus 3 times, this is going to be negative 2 plus 2 is a 0. So we're going to wind up with 14, it looks like. Negative 12 minus 2 is minus 14. The opposite of minus 14 is positive 14. So once we've done that, then we just determine what A sub 1, A sub 2, and in our case A sub 3 are. So X sub 1. So if you want to look at this, even in a vector format, if you want to look at it, the solution vector is going to equal, you get X sub 1, right, X sub 2, X sub 3, if you think about the solutions being the column vector. So we're going to get, just putting things together real quickly, each will be over the negative 2 from here. So each will be over the negative 2. And then we'll have A sub 1, which we calculated to be negative 20, A sub 2, which was a negative 4, and A sub 3 was a 14. So those can be simplified. And we're going to get the solution vector is negative 20 divided by negative 2, negative 4 divided by negative 2, and 14 divided by negative 2. So there's how you find the solution using Cramer's rule.